Hello, welcome to another module in this massive open online course. So, we are looking at source coding, various aspects of source coding, different kinds of source codes. In particular, we are interested in prefix free or instantaneous codes. And in the previous module, we have looked at an important inequality that has to be satisfied by the lengths of the code words of a prefix free code, that is given by the Kraft inequality. We will use this Kraft inequality to derive now a fundamental bound on the minimum possible average code length for a prefix free code. Okay. So, in this module we would like to focus again on the average code length. As I have specified before, this is one of the fundamental aspects of a code, that is we would like to characterize, correct, we would like to characterize the minimum possible average code length. What is the minimum possible average code length? We would like to ask this question. Again, towards this we would like to consider x drawn from a source with the alphabet S0, S1 up to Sm minus 1, and we have probability of each symbol Si is equal, probability of each alphabet Si is Pi, or each symbol Si is Pi. Now, the length we have seen, we have defined average length of a, so the average length of the code word let the length of code word I be Li. Then we know that for the average code length, or average code word length is nothing but expected value of L, which is I equal to 0 to m minus 1 Pi, that is the summation of the lengths Li weighted by the probabilities Pi, correct. This is expected value of this is the average code word length, which we are denoting by L bar. We have seen this before. The average code word length is summation Pi Li, I equal to 0 to m minus 1. And yesterday we have also defined, we have also seen the Kraft inequality, that the code word lengths of any prefix free code have to satisfy, and the Kraft inequality, which is a fundamental inequality which we had derived from a binary tree representation. Let me just refresh your memory. So, I have I equal to 0 I equal to 0 to m minus 1 2 to the power of minus Li less than or equal to 1. And now what we would like to define is, we would like to define this quantity Qi, which is equal to 2 to the power of minus Li by summation j equal to 0 to m minus 1 2 to the power of minus Lj, just changing the index using a different index. Instead of I am using j, because I am using in the I equal to j equal to 0, j equal to 0 to m minus 1 2 to the power of minus Lj. Now what can we say about this Qi? Okay, now we have defined this Qi. Now if you can look at this Qi, the first thing you will observe is that Qi is greater than or equal to 0. Okay, all the quantities involved are positive. Qi is greater than 0 since each 2 to the power of minus Li greater than or equal to 0, summation j equal to 0 to m minus 1 2 to the power of minus Lj is greater than or equal to 0. So, Qi is less than or equal to 0. Further we have 2 to the power of minus Li, each 2 to the power of minus Li, remember all the quantities are positive, this is less than or equal to summation j equal to 0 m minus 1 2 to the power of minus Lj, because 2 to the power of minus Li is one of the components in this summation. Alright, so all the quantities are positive and 2 to the power of minus Li is in fact one of the quantities in the components in the summation on the right hand side. Therefore, 2 to the power of minus Li is less than or equal to summation j equal to 0 to m minus 1 2 to the power of minus Lj, okay, which implies 2 to the power of minus Li divided by summation j equal to 0 to m minus 1 2 to the power of minus Lj, this is less than or equal to, let me just write this a little bit more clearly, this implies 2 to the power of minus Li divided by summation j equal to 0 to m minus 1 2 to the power of minus Lj less than or equal to 1, or rather this is in fact nothing but our Qj or Qi, this is Qi which is less than or equal to 1. So, we have Qi 0 less than or equal to Qi less than or equal to 1. Further, summation I equal to 0 to m minus 1 Qi equals summation I equal to 0 to m minus 1 2 to the power of minus Li divided by summation j equal to 0 to m minus 1 2 to the power of minus Lj. The denominator is a constant. So, we are taking summation over the numerator. What we have is summation I equal to 0 to m minus 1 2 to the power of minus Li divided by summation j equal to 0 to m minus 1 2 to the power of minus Lj, this is equal to 1. So, we have what we have is each Qi is positive, that is it is non negative, 0 less than or equal lies between 0 and 1 and summation of all Qi's is equal to 1. So, naturally the Qi's form a probability distribution, correct, form a probability mass function on this or from a probability distribution, correct. So, Qi's, correct. So, we have 0 less than or equal to each Qi less than or equal to 1, and we also have summation I equal to 0 to m minus 1 Qi equal to 1. So, Qi's form a probability distribution. Now, let us use the concept of the Kullback-Leibler divergence. Kullback-Leibler divergence which we have seen before. So, now we have a probability distribution Pi P0, we have a probability distribution P0 P1 Pm minus 1 Q0 Q1 Qm minus 1, and therefore the KL divergence between these, the Kullback-Leibler divergence between these two probability. So, we have two probability distributions, the KL divergence which is defined as D, which is equal to summation I equal to 0 to m minus 1 pi log to the base 2 pi divided by qi, this must be greater than or equal to 0. This is the KL divergence. Remember, we had looked at the KL divergence between two probability density functions. Okay, we had defined it something like this, the KL divergence between, for instance, if we have f and g which are two probability density functions, f of x and g of x, we had defined it for continuous probability density functions as two probability density functions corresponding to the random variable x as f of x g of x log 2 to the base 2 f of x okay. This was our definition for where f of x and g of f are probability density functions. Now what we are doing is we are again doing the same thing for discrete probability mass functions. P and Q are probability mass functions, correct, probability distributions on discrete symbols S0, S1, S minus 1. So what we have done is we have taken the definition of KL divergence which we have defined for probability density functions, and we have in fact now given the equivalent definition for probability mass functions, which is obtained by, of course, replacing this integral by summation, that is represent the continuous integral which is a continuous sum, replacing the integral by sum, and of course probability density functions by probability mass functions, probability densities by probability masses. So this is we have, this is basically the KL divergence for probability, you can say probability mass functions. Okay, so that's what we have over here. Now therefore we have the KL divergence greater than or equal to 0. Remember we said the KL divergence, and in fact we had established, we had rigorously proved using log concavity, right, using the concavity of the log function, that the KL divergence is always greater than or equal to 0. The same property, of course we had done it in the case context of probability density functions, but the same is also valid for probability mass functions. Okay, this implies that summation I equal to 0 to m minus 1 pi log to the base 2 pi log to the base 2 pi over qi greater than or equal to 0, which implies summation I equal to 0 to m minus 1 pi log to the base pi minus plus summation I equal to 0 to m minus 1 pi log to the base 2 1 over qi greater than or equal to 0. I can equivalently write in this fashion. Now if you look at this quantity pi log to the base 2 pi, you will realize that this is nothing but minus h of x, and now qi, remember, equals 2 to the power of minus li divided by summation j equal to 0 to m minus 1 2 to the power of minus lj, which implies 1 over qi is simply
summation j equal to 0 to m minus 1 2 to the power of minus Lj divided by 2 to the power of minus Li. So, log 2 to the base 2 1 over Qi, this is nothing but log to the base 2, well, summation j equal to 0 to m minus 1 j equal to 0 to m minus 1 2 to the power of minus Lj divided by 2 to the power of minus Li. The 2 to the power of minus Li can come to the numerator, so that becomes 2 to the power of Li. So, this is simply log to the base 2 2 to the power of Li, that is Li. Let me just write that also, log to the base 2 2 to the power of Li plus log to the base 2 summation j equal to 0 to m minus 1 2 to the power of minus Lj. Now, if you look at this quantity is nothing but Li. So, this will be Li plus. Now, if you look at this quantity here, we know from Kraft's inequality or from Kraft inequality we know that summation j equal to 0 for any prefix code 2 to the power of minus Lj is less than or equal to 1, which means implies naturally that log to the base 2 summation j equal to 0 to m minus 1 2 to the power of minus Lj, this has to be less than or equal to 0, correct. From Kraft inequality we know that summation j equal to 0 to m minus 1 2 to the power of minus Lj is less than or equal to 1. Therefore, if we take the logarithm of that quantity, the log has to be negative. So, I can write this as minus epsilon, where epsilon is some positive quantity. So, that is the whole idea. So, I can write this as minus epsilon, okay, where epsilon is some positive quantity, okay. That is the reason for that is because, so where what is minus epsilon? Minus epsilon is log to the base 2 summation over j 2 to the power of minus Lj, and therefore, this is equal to Li minus epsilon. So, now if we substitute these quantities here, this is equal to Li minus epsilon. And now, what we have interestingly is, if we call this equation as star, if we call this equation as star, from star what we have from equation star above, what we have is minus Hx plus minus Hx plus minus Hx plus, well, pi into Li minus epsilon minus Hx plus summation I equal to 0 to m minus 1 pi into Li minus epsilon is greater than or equal to 0 from the KL divergence implies summation I equal to 0 to m minus 1 pi Li greater than or equal to Hx plus summation I equal to 0 to m minus 1 pi into epsilon. Epsilon is a constant that comes out, summation pi which is equal to 1. So, this is simply Hx plus epsilon implies this is greater than or equal to. Now, epsilon is positive, recall epsilon is greater than or equal to 0, which implies this is greater than or equal to Hx. Okay, so, what we have, and this is nothing but L bar. So, what we have is L bar greater than or equal to Hx, which is the entropy of the source, that is summation pi log 1 over pi.
And there we have a very fundamental result, a fundamental bound on the average length of any prefix free code. Using the Kraft inequality, we have shown that the average length of any prefix code has to be lower bounded by the entropy of the source, and this is a very fundamental, elegant and interesting result. So, what this shows us is that what this is telling us is that the average length of any prefix code, thus we have a fundamental bound on average code length for a given source, and remember, not any code, average code length, we have to qualify this is for any prefix free code. Average code length for any prefix free code, and we have shown that this is bounded by the entropy. So, the average code length L bar greater than or equal to Hx, that is average code length, that is entropy is a lower bound. What this tells us, that entropy is a lower bound for the average code length. So, this is a very fundamental bound. What this says is, no matter what prefix free code you design, alright, since this has to satisfy the Kraft inequality, what that tells us is that the average code length cannot be lower than the entropy. At most it can equal to the entropy, it has to be greater than or equal to entropy. So, the efficiency of a code can now be judged by how close is the average code length to the entropy. So, we have a convenient means to just to judge the efficiency of a code. Remember, we said that lower the average length of the code, the more efficient it is, and now we have shown that you cannot arbitrarily reduce it to any non-zero quantity. This is lower bounded by the entropy. So, you can approach entropy, I mean one can desire or one can design a code to approach the entropy as closely as possible, but cannot of course make it lower than the entropy. And therefore, the closeness of this average code length to the entropy can be used as a measure to characterize the efficiency of the designed prefix free code for a given source. Alright. So, now how closely can you approach this entropy and how to approach it is something that we are going to see in the subsequent modules. Thank you very much.